we need the metric for. So today I would like to convince you that these conformal metrics with constant Q-curvature are good metrics for our manifold. I will start introducing you the Q-curvature and the panic factor. Then I will present you the constant Q-curvature equation and which the problems that equation has. Then we will study the Q-curvature equation on a product manifold because we want to avoid problems that the normal equation has. So then I will present you the main results, which are results of concentration of solutions for that equation. Briefly, I will show you the sketch of the proof. So a famous theorem in the geometry is the Gauss-Bonnet theorem, which states that for a two-dimensional compact manifold without boundary, if we integrate the Gaussian curvature, that quantity does not depend on the geometry of the manifold. That depends only on the topology of, because it's equal to 2 pi times the Euler characteristic of the manifold. So the question is, in higher dimensions, there is also another quantity as a Gaussian curvature with some kind of property similar to this one. Well, spoiler, it will be the Q-curvature, at least in dimension 4. But after going to the higher dimensions, I would like to show you some properties that has the Gaussian curvature. First, I will show you how it looks when we change the metric conformal. So a conformal metric to J is given by this J tilde is a positive function multiplied by the metric J, and it satisfies this relation. The Laplacian of the new metric, the conformal metric, is this function times the Laplacian. And the Gaussian curvature satisfies the relation between the new Gaussian curvature and the old one is given by this equation. So we are looking for not only a new function in higher dimension that plays the role of the Gaussian curvature, but also an operator like the Laplacian that satisfies a similar property to this one. So the Q-curvature was first defined in dimension 4, and it was defined in a closed Riemannian of dimension 4, and was given in this way, which depends on the scalar curvature, the Ricci tensor, and the Laplacian of the scalar curvature. So it's a geometric quantity. It's a scalar function because it goes from M to M. M is the manifold. And it satisfies a theorem known as Gauss-Bonnet formula, which is this one. If we integrate the Q-curvature plus 1/4 times the Weyl tensor to the square, we have a quantity that depends only on the Euler characteristic of the manifold. If we integrate some geometric thing, we obtain something that does not depend on the geometry, not the metric. And moreover, if the Weyl tensor is 0, for example, if the manifold is locally conformally flat, we get the expression that we were looking for. So this looks to be the right quantity, but we want a function in dimension bigger than 4. First, we will check that it satisfies the same properties that the Gaussian curvature. In this case, the operator that will play the role of the Laplacian will be the Panic operator, which in dimension 4 is defined in this way. This is a 4-order operator driven by the bi-Laplacian minus another term. For example, to simplify a little bit this operator, we can think on the round sphere, the sphere with the metric round, and it looks like the bi-Laplacian plus a constant times the Laplacian. It satisfies also a conformal property, because if we take a conformal metric to G, it satisfies this relation, which is very similar to the relation which satisfies the Laplacian in dimension 2. And also we have the relation between the new Q-curvature, the old Q-curvature, or the original Q-curvature. And it's also a relation very similar to the relation between the Gaussian curvatures. So now we are trying to see if this happens in higher dimensions. So for dimension bigger than 4, Branson, 2 years after than Panitch, defined these quantities. The Panitch operator in dimension bigger than 4, which is very similar to the 4-dimensional case, but now we have an extra term which involves the Q-curvature, a new Q-curvature with for the dimension bigger than 4. The expression is almost the same, but the constant depends on the constant change. It depends on the dimension of the manifold. So again, we can think on the Panitch operator on the sphere. Many things will be simplified. We will have the bi-Laplacian plus a constant times the Laplacian plus u in the case of the Panitch operator. It also satisfies a conformal invariance property, but this time the exponent on the function will be different. Here it will appear the critical Sobolev exponent, -1. And if we pay attention here, if we take the constant function u in the Panitch operator, here should be phi. If phi is equal to 1 and u is equal to phi, all those terms will be 0 and only survive the last term. So it only times a constant. So we will have this relation. If we take phi equal to 1 and rearrange the things, we will get this equation, which is the relation between the old Q-curvature, because here is hidden the Q-curvature of the metric change. Again, we can think on the sphere. The Panitch operator is simpler. It's easy to remember. So this will be the equation that we would like to study. Remember that we are looking, we will be looking at a conformal metric with constant Q-curvature. Well, for those who know about the Yamabe problem, this is a very similar problem. So we can ask the same question that Yamabe did for scalar curvature. We can ask if we can we find some Q-curvature metric in a given conformal. The question is equivalent to find positive solutions to this equation. If we find u a positive solution to this equation, we can build a conformal metric with constant Q-curvature given by lambda. So this is the equation that we would like to study. But this equation, we can expand the Panitch operator, and it looks it has some problems. First, in the right side, we have the critical Sobolev exponent. So we lack the compactness, similar to the Yamabe problem. But now we will have an extra problem, is the presence of the bi-Laplacian. It will appear, that will give us of maximum principle. remember that we are looking for positive solutions, so the maximum principle is essential. And moreover, there is no guarantee about the existing solutions for the equation yet. So I will tell you some existing results briefly. The existence, similar to the Yamabe problem, will be given by proving that critical points of this operator are solutions of the equation. So what people is trying to do is to prove that this infimum is in fact a minimum, so we can guarantee size the existence of a critical point. Well, in some cases, it is proved. There are some results when the manifold is locally conformally flat and has positive scalar curvature. In the first case, we have an extra condition. Then Ebe and Robert remove that condition. This result is about Gursky and Peschiodi, and that there exists that minimize that functional. In the case where Q is non-negative and positive somewhere, and M has non-negative scalar curvature. That is the best scenario when the Q curvature is positive or non-negative, and the scalar curvature that can guarantee the existence of solution, of a positive solution. There is here another existence, but under the same conditions or almost the same conditions. And an easy case is when J is an Einstein metric, it has constant Q curvature. It can be an easy exercise. Well, so we have three main problems: the lack of compactness, the lack of maximum principle, and we don't know if there is a solution. To avoid this problem, we are not going to solve them, but we are going to avoid them. We will work on a product manifold. So we will consider M a closed dimensional Riemannian manifold, X a closed n-dimensional Einstein manifold with positive Einstein constant. That condition is only to simplify the computations, but we don't know if it works if we don't put that condition. And we consider the Riemannian product M times X with a metric given by J plus epsilon to the square times, which has a little perturbation of the second metric. Well, we have some assumptions about the dimensions of the manifolds. So, well, on a product manifold, under these conditions, the equation on a product manifold, the Panning's equation, will be very long. But if we ask that for a solution, we look for solution that depends only on the first manifold, it will simplify a lot. And the equation will look like this: the main term, the bi-Laplacian times epsilon to the 4. And in the right hand side, we will have u to the critical power for the product dimension. N is n plus n. So that will solve our first problem. This critical exponent will be, this is an equation on M, and this critical exponent will be less than the critical on M. So we also add this hypothesis that M is flat, also a little bit more the equation, and we get this constant Q curvature, which is simpler, with an exponent on the right hand side, which we call Q, which is a sub-exponent. So this is the equation that we are looking for solutions. Now we will show that there is at least one solution to this equation. And using the theorem of Gursky and Malchiodi, they proved that if the Q-curvature is semi-positive and the scalar curvature is non-negative, then we can find a positive solution to our equation. So in our case, if epsilon is small enough, the scalar curvature will be the sum of the scalar curvature of the first manifold plus 1 over epsilon to the square, the scalar curvature of the second one. So if epsilon is small enough and this one is positive, we can be sure that this quantity will be non-negative. And the same thing with the Q-curvature longer. So thanks to Gursky and Malchiodi, we know that there is at least one solution, which is a minimizer of the function. What we did in our work is to build another solution, a solution which concentrates energy at one point. So that's why it will be a different, because this is a minimizer of the energy and our solution will be not, we have. So I will present you now our results. Well, our main theorem states that under all the hypotheses that I mentioned before, if C sub 0 is an isolated minimum or maximum point for this function that depends on the metric tau sub g, continue or not? Okay. Well, so given a minimum or maximum point of this function tau sub g, then for all epsilon small enough, our equation has a solution u sub epsilon, which concentrates around this point. This is a geometrically relevant point because it's a critical point of a geometric point. So here, the exponent is the same as before. It's a subcritical exponent. Okay, and as a solution to that solution, we can build a conformal metric to the original one, which has constant Q-curvature. So the corollary is immediately what we were talking. So to finish, I will sketch the proof. To build a solution that concentrates around this geometrically relevant point, we will consider an equation in the Euclidean space, which is very similar to our equation with some constants here, B and A. And we will study solutions in Rn. A and B are positive constants. The exponent is subcritical. And we will call this equation but we didn't get this taking the limit of epsilon going to 0. In original equation on M, we have the epsilon involved in this one. This is independent of epsilon, but it has some properties. First, we can, if B is bigger or equal than 2 times the square of A, there is a positive solution. that satisfies that U is radially symmetric around some point. U also is strictly radially decreasing and exponential decreasing. And moreover, all his derivatives are exponential, have exponential decay. And if U sub epsilon is given by U in X over epsilon, then this new function U epsilon is a solution of our equation, but in the Euclidean space. So it's a very close to our equation. What we want to do is to take this equation in the Euclidean space, which concentrates around the origin. It's always positive. We will use the metrical exponential, and we will go to the manifold. And we will build a solution that concentrates its energy around a point that we need to choose one. So to this end, we will need a very strong assumption, but it is not proved yet, but I think it will be proved soon. The assumption says that that solution has the non-degenerate property, which means that all the solutions to the linearized problem are given by its derivative. And those are all the solutions of that new equation. This is a stronger assumption, but it is proved in some dimensions, and also it is proved for some special constants, B and A. So we think that it will be soon proved in general. Also, it is proved in the case of the two order equation without the bi-Laplacian. So we think that it's not a very strange hypothesis. So we will build the approximate solution in this way. We use the geometric exponential function to bring points from the manifolds to the Euclidean space. We compose with our function U, and we multiply by a cutoff function, be all well defined. So these functions will be our approximate solutions. Then we need to define the space where we are looking for solutions. It will be the Hilbert space given by H2 with this norm. It's not the usual norm, but it's equivalent because it has this constant here, A and B. And we split this space in two spaces, which is theta is generated or is spanned by these thetas A, I, which are given by the partial derivatives of function U. Those are familiar or similar to these ones. So that's why we need the that assumption and the orthogonal complement. So we have a finite dimensional space and another space of infinite dimension. So we are looking for a solution U that is close or similar to our approximate solution. The difference between U and W will live in this space and has to have not very small. So here we have our equation again. We will call J the functional associated with this equation. And we will define J bar, which is the functional J with W, our approximate function concentrated on a point C, plus a function phi that we can prove that this function phi exists for each psi using fixed point theorem. So we can prove that this function always exists, phi depending on xi, and in that way we build this new function that goes from the manifold to R. If we evaluate this function J bar on the point we are concentrated our approximate function, we get this new function J bar. Well, what we prove, which takes a lot of computations, is that J bar can be approximated by this quantity. We can reduce expression of J bar to this one. So critical points of J bar will be close to critical point. Moreover, critical points of tau sub G will give us a solution of our problem of the form W plus phi. So what we prove is that there is always a critical point of J bar in a neighbor of this C sub 0, which is